Balancing equations. All right, so I want you to define a word first of all, which you can see up here on the board. Is mole. We give a very simple definition to start. A mole is an amount of a substance. It's an amount of a substance. It's a very basic definition. An amount of a substance. It's not a small furry critter or furless critter as a naked mole rat. Nor is it a spy. It's an amount of a substance. Yes.
Wait, should we write down the ask and here part?
Yeah. Where we get a mole is based upon 12 grams of carbon-12. All right? And so basically, this is the number of atoms in 12 grams of carbon-12. Now, why is it based on carbon? Carbon is the basis for all life, and so carbon is very, very important. It's a very interesting element. And so we use it for a lot of things. We haven't used carbon much in this class because we're not on that right now. But it forms all organic compounds, so it becomes very important. So this is the basis for how we get the concept of moles, and we have Avogadro's number, which we're not going to get into this class, but it's basically how, right? You're laughing, right? Basically that number of atoms, all right? Which is what, Haley? What's the number? 6 point times 10 to the
-8.
Yeah. All right, so we're not worried about that right now. Oh, you're trailing off. We're not worried about that right now. All I need you to know right now is an amount of a substance based on carbon, and we use it for ratios in our chemical reactions. All right, and we're going to use a ton of that in stoichiometry starting tomorrow. We're kind of doing the entry today, and we'll get into more of it. Right, but we're going to use it as amounts for our ratios in chemical reactions. Now, we'll give a very simplistic example of where we're going. If I have a recipe, and this recipe says 1 cake requires 3 eggs, 2 cups of sugar, 1 stick of butter, 2 bars of chocolate, 3 scoops of joy. All right, and that's my. One flour. Look, that's the best thing I've drawn all year. All right.
Why your leaves so
Thank you.
flimsy?
All right.
Is it dying?
It's got 6 petals, so it's a monocot, just so you guys are aware. So this is our recipe for a cake, and I said, hey, can you make 3 cakes? And you all could easily do that, right? We would say, okay, well, we're going to need 9, we're going to need 4, we need 2, right? 9, 6, easily. 9, 6, 3, 6, 9, 3, right? We need 3 flours to make this. Right? You guys could easily do the multiplication and figure out what we need for 3 cakes. Now, if I gave you ingredients and said, hey, we've got 9 eggs and 5 cups of sugar, and I got 3 of these and 4 of these and 9 of these and 2 of those. Could you tell me how many cakes you could make?
No. Yes.
Yeah, you could, right?
But you would have to have enough same.
You're not going to have enough of everything, so you can tell me which one's going to limit you, right? Right? Like I can make 3 cakes out of this, but
Only
2 and a half, depending on how I'm doing my recipe. 3 there. I can only make 2 out of this. So because I only have so much chocolate, I can only make 2 cakes, right?
Yeah.
And so that would be our limiting reagent. That's going to limit how many cakes we can make. All right? And so what we want to learn how to do is how to look at a chemical reaction and see how many of each element we have and see how much product we can make, or look at how much product we need and see how many ingredients we need to go buy. All right? And so that's what we're going to kind of figure out how to do this with chemistry. All right? So here we go. Right? So balancing equations. We're going to start with a simple example. NaNO3 NaNO3 plus PbO yields PbNO3 2 PbNO3 2 plus Na2O. Na2O. Now, a couple of things you ought to be able to do right away. You should be able to tell me what kind of reaction this is, or at least after you studied them a little bit, you should be able to. What kind of reaction is that?
Single displacement.
Metal, polyatomic, metal, polyatomic. Or, non-metal. We're just switching the nitrate and the oxygen, right? So that is we're switching them onto different metals. That would be double displacement. All right? It's a double displacement reaction, and you should, in theory, be able to name all these, right? Sodium, nitrate, lead, oxide. Now this would technically be lead 2 oxide. It's a transition metal. And you know it's lead 2 because of oxygen. Lead 2 nitrate and sodium oxide. All right? So when you're hanging out with your friends this weekend, you're like, we were just looking at some double displacement reactions of sodium nitrate and lead 2 oxide today. It was fun. It was good. Good times. You guys should be able to read that and know what it says and know what's going on. All right? Now, let me erase this and get back to the purpose here of balancing equations. What I want to do is I'm going to list these in order that they appear on this side. Now, this practice that we're getting ready to do is something that I want you to learn how to do, but you're going to get rid of it once you learn how to do it in your head. You'll learn how, by the end of the day, you should be able to do it in your head and you don't need to write it down anymore. All right, so sodium, nitrogen, oxygen, and lead are my 4 elements on this side of the equation. I like to write mine twice. I like to write them over here as well. And I like to write them in the same order. Na-N-O, Pb. Sodium, nitrogen, oxygen, lead. Some people will write them in this order, whatever order they appear on the right side. It's really a preference thing. I like to keep mine in the same order. That way I can look straight across and see them. Okay? So I write them the left side, then I write the right the same as I did to the left. Some people will write them in order again. All right. Now, how many sodiums are on the left side of the equation? In the reactants, how many? 1. How many nitrogens?
2.
1. Just this one? How many oxygens?
3.
4. Right? We have 3 here, and that one down there. 4 oxygens. And how many leads down here?
1.
Just the 1. How many sodiums on the right side?
2.
I have 2 sodiums over here. How many nitrogens on the right side? 2, right? I have nitrate twice. I need 2 nitrogens. How many oxygens on the right side? 7. I have 3 here, but I have it twice. That's 6. 7. And how many leads over here? 1. Okay, so we have to conserve these. Whatever I put into a reaction, I have to get out. So what we're going to do now is we're going to add coefficients, like math class. We're going to add integers to multiply these by to the front of each compound so we have the right number. Basically, we're going to look at how many of each ingredient we need to make this happen. All right? So I like to start at the top usually. So I have 1 sodium right now. How many sodiums do I have over here?
2.
So what do I have to do to the sodiums over here? I have to double them, right? So I'm going to double this. Boom. I had 2 of that compound, 2 sodium nitrates. Now, I now have 2 sodiums, but if we distribute that 2, I also now have 2 nitrogens, and also now have 6 plus, oops, wrong one. I now have 7 oxygens. Is my equation now balanced?
Yes.
Do I have the same going into the equation as coming out of the equation? Yes.
Wait, how come the 2 doesn't go to the...
It only goes to the compound it's with.
Oh.
Just like if we were doing multiplication, we had 2 in front of parentheses or something. It goes to that compound alone. All right? Now, if there's nothing there, we assume it's 1, right? We don't have to write that. I'll write it this time just so you can see it. It's assumed that there's a 1 there. So now we have a balanced equation. We have 2, all right? So we would read this. This is the number of moles. So 2 moles, 2 amounts of that substance. I have 2 moles of sodium nitrate plus 1 mole of lead 2 oxide yields 1 mole of lead nitrate, lead 2 nitrate plus 1 mole of sodium oxide. All right? Think of it just like a recipe. This is how many of those I need to get that product out. If I want these cakes, this is what I have to put in. All right? Let's look at another one. Didn't even have to add any flowers to that one. All right. Fe plus AgNO3 yields FeNO3 2, FeNO3 2 plus Ag. Katie, read that equation.
Iron plus argon.
Nope. Somebody else. Caden. This Caden. Girl Caden.
Iron plus argon nitrate.
Nope.
That's silver.
Alex Holland-Blitzel.
Iron plus silver nitrate yields iron nitrate times 2 plus silver.
Nope, just iron nitrate. You don't need to say times 2 plus silver. And we should know they are transition metals, but you don't know those off the top of your head, so that's fine. So iron plus silver nitrate yields iron nitrate plus silver. And this is what type of reaction, Caden Dozier?
Single displacement.
Single displacement. We just switched the nitrate from the silver to the iron. All right? We displaced one thing over to another place. All right, now let's list our elements. Fe, Ag, N, O. Fe, Ag, N, and O. And to start, I have 1 iron, 1 silver, 1 nitrogen, 3 oxygens. And in my product, I have 1. I have 1. How many nitrogens do I have? 2. 2. 2 nitrates. And how many oxygens? 6. 2 times 3. All right. Switch markers here so you can see the changes. So I like to start at the top. It's just easier for me. So iron is good. Silver is good. Nitrogen. I need to double my nitrogen over here, right? So I'm going to double it. So I have to double this whole compound. All right, so now I have 2 nitrogens. Problem is what? 2, oh my goodness, right here, argon again. 2 what?
Silver.
Silver. And I have how many oxygen now?
8.
2 times 3. 6. Gilbert. She's not here today. She's at that surgery for anatomy. Bye. All right, so now I've gotten this, so my iron's still good, and this is good, and this is good. The problem is I now have 2 silver, but over here I only have 1, so I need to double my silver over here, which is pretty simple, right? 2 Ag. So we could say this is a single displacement reaction. 1 mole of iron plus 2 moles of silver nitrate yields 1 mole of iron nitrate plus 2 moles of silver. Ireland.
On the first one we did,
Yes.
why does the left side have 3 moles, but the right side has 2?
Doesn't matter.
The mass doesn't have to be.
No, the mass is the same. The mass is identical. This makes the mass the same. Putting these here makes the mass the same. So this total mass of these things is going to equal the total mass of these things. There are 2 nitrates here. There's only 1 nitrate here. Does that make sense? So that the number of atoms there is greater. So we double it. So ultimately it's going to come out the same. What we're doing is making it balance, is making it equal. Good question. I don't think I've ever had anybody ask that question, but it's a good question. Okay. Let's look at one that's slightly more complicated. These aren't too bad, are they? Look at one that's slightly more complicated, and then I'll turn you loose on some of your own. All right. Let's do AGI plus Fe2CO3 Fe2CO3 yields FeI3 plus Ag2CO3 Ag2CO3. Stetson.
Yeah.
What kind of reaction is that?
One second, I have to figure it out. I have to first have to finish writing it down.
Brittany, what kind of reaction is it?
Double displacement.
Why?
Because two things move. The I moved to the FE and the CO3 moved to the AG.
Very good. Double displacement. We took the 2 things, the 2 non-metals, and switched them over to the other 2 metals. All right. Double displacement. Holtkamp. Read it. Nope. Oh my gosh. Somebody else. Let's see. We got Myros. Read it.
Silver. Like on
Oh, you didn't have to memorize that, did you? Iodine. Silver iodide.
plus iron. Do I have to say it?
Polyatomic ion. What is it? Oh, I see what you're saying. No, it's fine for now. Silver iodide plus iron. CO3 is what? Somebody? Carbonate. Iron carbonate yields iron iodide
Iodine
plus
silver to whatever you said it was.
carbonate.
Carbonate.
It'd be silver 1 carbonate. All right, so silver iodide plus iron carbonate yields iron iodide plus silver carbonate. Makes for a good time. All right. A-G, I, F, E, C, and O. What's different about this one? First of all,
Has 5.
we have 5 things to balance. They get much more complicated than that.
Wait, they don't get very much more than 5.
We won't, you'll have some combustion reactions. You have one on your work today that goes up to 30 of something. But aside from combustion reactions, we don't go above very many moles of anything or very many elements. All right. How many silvers on the left? 1 iodines, irons, 2 Fe2, carbons, 3 oxygens, 9. 3 sets of 3. Over here I have 2 silver, 3 iodine, 1 iron, 1 carbon, 3 oxygen. So we got a long ways to go here. A long ways to go. You guys remember that whole least common multiple thing, right? Okay.
Oh, we're defining.
Least common multiple, greatest common factor. Which one's which? We need to find out what number they both go into. It's that least common multiple, isn't it?
Yeah.
All right. Let's start at the top. Silver. What can I do with silver? If I multiply it by 2, I doubled that. I now have 2 silver, but I also have 2 iodine, and then we should immediately see a problem. I got my silver good, but I go down to my iodine. What do I have? I have 2 and 3. Is there any integer I can multiply 2 by to get to 3?
You can do 2 times it. There's no way there would be 2 x's and then without adding 2 i's.
I can't multiply this by any integer to make this 3. I put a 3 there, but then my silver's off too. So what do I got to do? I need to find a number, because I can't change this. This can only increase, right, if I'm multiplying by an integer. All right? So I need this. What is the number that these both go into? 6.
So multiply 2 by 3 and...
So let's change this to 6. Let's do that. We'll multiply that 2 by 3. Let's make that a 6. So now I have 6 of those, and I have 6 of those, right? 6 silvers and 6 iodines on the left. And what we did that for was so we get to the same number as iodine. All right, so I got to find here this iodine, right? So I have 3 of it. How do I get to 6?
2.
Multiplied by 2. So now I have 6 iodine, but I also have 2 iron now, right? Okay. Now what's wrong with my silver? I've gotten this fixed, and I fixed this in the meantime, but my silver was messed up now. I need to multiply it by 3. It's a 2. I need to multiply it by 3. So I put a 3 there. Now I have 6 silver. I also now have 3 carbon. And also now I have 9 oxygen. This is a double displacement reaction with 6 moles of silver iodide plus 1 mole of iron carbonate, yielding 2 moles of iron iodide plus 3 moles of silver carbonate. It's exciting, isn't it?